two parts to this question really. A and B, which are all about the differential equation, and then C and D, which are about solving an equation using an iterative method, so numerical methods. I'm just going to focus first of all on A and B, then we'll come back to the numerical bit. Okay, we're told that the car is moving following this formula. A is the acceleration, B is the velocity, and we're asked to find times when the acceleration is 0. So A equals 0. Remember, V is greater than 0, so A is actually 0 when 8t over 7 plus 4t squared minus a half is equal to 0. That's the only way it can equal 0. So that means this thing here is going to equal a half, and then I can times through by 7 plus 4t squared. Get rid of that. I'm also going to times through by 2. I could expand the bracket, but it's much better to times through by 2. 16t is then 7 plus 4t squared. Okay, we've got ourselves a quadratic. 4t squared minus 16t plus 7 is going to equal 0. And you can either, well, we'll have to show detailed reasoning, actually, so do not put this in your calculator, or if you do, factorize it at the very end. So I'm going to go with 2t. I mean, look, it might take a little bit of time to factorize, but 2t and 2t, they're going to have to both be negative. If I make it minus 7 and minus 1, then it all checks out. T is going to equal a half, or 0.5, or 7 over 2, 3.5. If you're struggling with that aspect, I do show this in quite a few of my videos, but just get the quadratic formula out. Just kind of don't tell people that you're doing it. So I just accidentally got myself a quintic there. Okay, quartic, sorry. But yeah, back to quadratic. 4 minus 16, 7. Okay, we get 7 over 2 and a half, and then you kind of have to reverse engineer it. So we've got t minus a half and t minus 7 over 2 when you're factorizing. But we know we need a 4 there, so we're going to times this by 2, which will give you the same root, and this by 2. So that's how you can do it if you're struggling. And then write it down. But I would advise, I haven't actually checked the mark scheme, but I think it's just good practice to write it in factorized form. Or if you do want to, use the quadratic formula, but write it out, okay? Because it does say detailed reasoning. I just wouldn't leave anything to chance. So those are the times, right? We're now asked to set up and solve a differential equation, show that t satisfies this equation. Okay, there's a few, do you know what? I'm just going to bring the whole question down again. Few things to write down here. First up, we do have a differential equation. A is the rate of change of velocity with respect to time. So I can write down that dv by dt is equal to v times 8t over 7 plus 4t squared minus a half. But we've got some other information. We're told that when t is equal to 0, that v is 17.5, and then t is equal to a capital T when v is equal to 5. And that's the one that we're interested in, trying to solve for the time when the velocity is 5. A differential equation with v and t in it, we cannot integrate this directly. We need to use separation of variables. So I can divide through by v, or multiply by 1 over v, get it onto the left and away from the right. And then you've got a couple of choices. You might be somebody who timeses both sides by dt and then sticks an integral sign around it. Me, I like to say, right, I'm integrating both sides with respect to t. And that gives us this. It's just that using the chain rule, this becomes dv. Let's integrate. We've got ln modulus of v is equal to, okay, now I've got to integrate this. It's a fraction. It's not going to be partial fractions or anything like that. It doesn't easily factorize. The first thing to actually look at in this situation is it in the form f f dash t in this case over f of t. Because if it is, then you can simply write the answer straight down, ln of the modulus of f of t. Reason being, when you differentiate ln of a function, you differentiate the outside, the ln bit, you get 1 over f of t. Then you times by the derivative of the inside, that's your f dash t. So this is a result to just know, be ready to look for. And it's precisely the result here. If you differentiate 7 plus 4t squared, you get precisely 8t. So I can simply write down that it's ln. You could do a substitution, by the way, like u equals 7 plus 4t squared, but no, I would say be on the lookout for this for sure. Because actually it's very quick then. That, and then minus a half t. And then we've also got a plus c. Now I'm going to sub in some of these conditions. We want to work out c first of all. So sub in this one. Ln, wait, let me just say that's what I'm doing. When t equals 0, v equals 17.5. This implies ln 17.5 is going to equal ln 7 plus c, which means c is going to be ln 17.5 minus ln 7. That's just ln of 17.5 over 7. Oh, I had it in the wrong mode. 17.5 over 7. Okay, 5 over 2. I'm going to write it out again. I could absorb it into the ln. I'm not going to do that quite yet. We're going to look at the next bit now. Just going to bring down what I'm trying to get. And then I'm going to use the fact that t is capital T when v is equal to 5. Have this in the background. So now I can say that ln 5 is going to equal ln 7 plus 4t squared minus, minus a half t plus ln 5 over 2. What I can do is rearrange it slightly. So I'm going to get a half capital T is equal to ln 7 plus 4t squared plus ln 5 over 2 minus ln 5. And you could combine them separately, but I'm just going to go for it. It's going to end up being 5 over 2 times 7 plus 4t squared, combining the logs here, all over 5. The 5s are going to cancel. And that means that t is going to equal 2 ln 7 plus 4t squared. And if I'm halving it, it's the same as dividing by 2. And the only thing that I've done there that I haven't explained actually is I had a modulus sign around the ln with the t squared in it, but it's always going to be positive, so I don't actually need it. Okay, that's why I could just get rid of it. Okay, we're nearing the end. We're now on to the second part where it becomes a numerical approach to solve this equation using an iterative formula based on the equation in part B. They didn't give it to you. Find the value of t, but actually it's basically set up for us because what we can do is just make it t n plus 1 equals 2 ln 7 plus 4 tn squared over 2. Because what I'm actually doing is instead of sort of solving just a single equation, I'm plotting y, this is y up here, and y equals t, against whatever this ends up looking like. I'm not really sure. Um, let's draw it like that. And then we're going to put in a value of t. So that's my kind of starting value, work out the function, and then that becomes my new value, spiral around hopefully or something like that, and converge towards the solution. This is called fixed point iteration. So basically, I've roughly explained how it works. We can write this down as our formula. And we're told that the initial value to try, t, let's call it t1, is 11.25. And then we just put it in, get a value out, and we just keep doing that basically. And we're looking to get our answer correct to 4 significant figures. So here's the process. We do 11.25 equals, stores it as the answer button, becomes 2 ln 7 plus 4 times the answer squared over 2. This will give us our next value. We just need to keep writing them down. So 11. So I'm going to write it down to 4. I think what I did was 4 decimal places actually, just so I could keep track of the convergence. 11.0952. And then you just keep pressing equals because it will now, this is now my answer. Such a great function. Okay. This is what I did earlier. I'm going to write them all out. 0405. Remember, I want it correct to 4 significant figures. The 4th figure is still changing. Still changing. Yeah, at this point it didn't change. And so I just kind of just kept pressing equals and seeing, yeah, okay, that's actually the converged value. I don't even need to write that down, but t is going to therefore be 11.01. Finally, we're actually given the velocity time graph, and we're asked to find the time taken for c to decelerate from traveling at its maximum speed here to when it's traveling at 5 meters per second, maybe sort of down or around about here. Remember, we've just worked that one out, 11.01. I'm not going to worry about using a full figure or anything because I'm going to give my final answer to 3 significant figures for this next bit. Okay, so it's asking us for when it was traveling at its maximum speed. That's actually when the acceleration is 0, which is what we did in part A. We found out that the acceleration was 0, or dv by dt was 0. That gives us a maximum for the velocity time graph when t is 0.5 or 3.5. So 2 different values, but you can see there's a minimum here. That is going to be the 0.5, the lowest one. The maximum is then going to occur at 3.5. So the time taken to decelerate is going to be the difference. 11.01 minus 3.5. And that works out nicely to be 7.51 seconds. All right, good question. I like the combination of the differential equation, a little bit different with the numerical method at the end. Good job.